Okay, so we're back. We just left off talking about local effects of temperature, air temperature, and I introduced the concept of the urban effect known as the urban heat island. So we identified that surfaces in urban areas are darker, less reflection takes place there, so more absorption. There's less forest cover, less vegetation, less grasses, less water on the surface to help absorb and distribute that energy due to the different specific heat. And this is going to be technically location and environment that is defined by humans' energy, where we're building, we're putting concrete and asphalt in locations. We went ahead and introduced the sketch of an urban heat island. So the red line looks at the temperature line, and we're looking at a late afternoon temperature. Typically, the highest temperature takes place around 2 p.m. A little bit of a lag effect from when the sun is highest in the sky, because of the absorption and re-radiating that heat out and warming up the air. So we see that the temperature moving from left to right on our diagram here depicts that the temperature is lower over rural areas, and as we start going into more urban residential areas, the temperature line peaks up to 92 degrees. Again, this is a good indication that we're having some temperature fluctuations due to the surface of the urban area, due to the cities. And then as we move into the suburban residential areas and rural farms, the temperature goes ahead and fluctuates and reduces. Now, another factor that I want you to think about is we're also seeing the effects of these urban heat islands in fog. And I was part of a research project for my master's degree where we were looking at and measuring these fog holes that would take place in Modesto and Fresno down in the Central Valley. And for those of you that are not familiar with this region of the world, the winter months are very foggy in the Central Valley. And this is when you hear about those major, car pileups because of thick fog. And it's a natural, weather factor that takes place due to the surrounding atmospheric conditions, and the fog is very valuable for the surrounding vegetation. Lots of crops get their moisture from the air. And so what we're finding is that due to cities such as Modesto and Fresno, due to the fact that they're growing, their physical footprint of the surrounding city is growing, we are seeing effects that from the heat island that are influencing the fog bank overhead. And so as a result, these urban heat islands are actually burning holes within the fog bank overhead. And you can measure these fog holes, or as the primary author of this paper coined them as urban clear islands, because they were clear from fog. These fog holes literally match the urban footprint. So they match the urban heat island. So, it's very interesting to think about, how temperature and how, surface material can influence not only the surrounding air temperature, but how that surrounding air temperature can influence the lower atmosphere, such as, things such as clouds and fog that take place within the troposphere. So pretty amazing. Now we can go ahead and look at the radiant energy flowing, and as that relates to different times of the day. Now, as we identify, we said that the sun is highest in the sky around noon, but really the warmest temperature that we see is around 2 to 3 p.m. Due to the fact that it's the energy from the sun is being absorbed by our surface and then re-radiating out, which is also heating up that air. And so there's a little bit of a lag effect from when we identify the highest absorption of the insolation, and then as that insolation is reheating up the air temperature. And so it's important to realize. Okay, so we went ahead and talked a lot about the annual range of surface temperatures. We know that, if we had to paraphrase this, we would say that, we have consistently warming temperatures in the tropics and the equatorial regions near water. We could also describe that higher altitudes are cooler than surrounding lowlands. We know that high latitude continents in the northern hemisphere have the greatest annual range in temperature, especially if you're away from water. And more maritime influence in the southern hemisphere gives us a smaller annual temperature range. So this is kind of a nice summary of everything that we talked about when talking about the surplus of energy along the equatorial regions, the different heating properties of land versus water, and then also applying altitude. So now we're going to go ahead and we're going to start talking about and integrating how the Earth is able to distribute that surplus of energy along the equatorial region. And it's done through atmospheric circulation and through these features that we will be talking about called atmospheric pressure systems and wind. And so key factors that we will be talking about is pressure systems, the direction of airflow, global pressure in atmospheric circulation, local winds, and oceanic circulation. Now, we identified the 4 specific layers of the atmosphere, and we said that, you know, temperature changes and pressure changes as we move higher up. So remember, for us standing on the Earth's surface right down here, we have so much pressure, so much of this atmosphere that's pushing down on us, pressure. And so if we literally had a scale to measure atmosphere, that amount of force that atmosphere is pushing on the scale, and we were able to measure that, we are measuring the weight of the atmosphere. And as you're moving up in the atmosphere, the weight gets less and less and less. We talked about how the distribution of molecules are reduced as you get higher up. Now, this is a very important concept to think about. So as you're standing on the Earth's surface, there's pressure pushing down on you. Now, air pressure we define as the force that air molecules exert on the surface due to their weight. Okay, so we just went ahead and we defined air pressure. So it's the weight of the air that's pushing down on the surface. So it's the weight of air on the surface of the Earth, and air pressure decreases with altitude. We do know that just by observation and measurement that warm air is lighter, less dense. And cold air sinks, so we define that as being more dense. Okay, so let's go ahead now look at this schematic diagram looking at pressure and altitude. So if we were to go ahead again, measure along the Earth's surface, we would define using our terminology that we just talked about, that it has a higher density and a higher pressure. And as we move away from the Earth's surface with increasing altitude, we would have a lower density and a lower pressure. Now let's just go ahead and talk about measuring and mapping air pressure. So air pressure is measured in millibars, okay, and it's measured by an instrument called a barometer. Now, the barometer was first invented by a scientist with the last name of Torricelli, and he used a long glass tube, and that tube sat in a pool of mercury, and with a little container of mercury, with the tube sticking straight up. And he was experimenting with this somewhat of a vacuum approach to see what would happen throughout the course of the day, throughout the course of the week, to see how that mercury moves up and down the vacuum of that glass tube. And so what he noticed is that as certain changes in the weather would take place over the days that he was monitoring this and observing this, he noticed that the value of mercury in the glass tube would go up and down. And so he was able to create a scale on the side of the tube to measure what these changes, observational changes, were taking place. And he noticed that these changes are taking place also correspond to the changes in the weather. And so what he came up with was the fact that this pool, the pool of mercury that we see in the bottom here, is basically measuring the change of air pressure that was pushing mercury up and down the scale of this glass tube in this vacuum. And so it was a measurement of air pressure weight that was able to be measured with this glass tube. So it was a pretty amazing discovery that this was the first barometer that could determine changes in air pressure, but had a very quantitative approach to it where we can actually see the change and measure those changes. So when we go ahead and we look at air pressure, we know that it's a collective weight of the atmosphere, and it's measured in millibars. And so millibars, remember, is the unit of measurement for air pressure, and a standard millibar measurement at sea level is 1013.2 millibars. Now, oftentimes you can see that depending on which discipline you're in, the units of pressure changes. So it can be described, our 1013.2 at sea level can be described as 760 millibars of mercury, or it can be described in 29.92 inches. And this is just a different unit for describing what we're measuring here, which is going to be the air pressure. And the barometer gives us the difference in air pressure, and that measurement determines how we have winds. So differences in air pressure creates winds, and we're going to be talking about that in great detail. Now, we depict winds on maps. We draw winds on maps using a map symbol called a ISO line, or more importantly, we actually map pressure systems with ISO bars. Okay, so ISO bars are going to be lines connecting equal pressure values. So going to our weather maps, we will see areas of high and low pressure with lines connecting the two, which I'll have an example in just a little bit. Okay, so when we talk about pressure and density, so air pressure is the weight or force of the atmosphere that's pushing down on you. And again, we talked about as you move higher and higher up into the troposphere, the stratosphere, the mesosphere, you're going to have less pressure on you. And as a result, you're going to have less atmosphere as well. So we can see, looking at the picture on our right, for a town such as Bombay, located at sea level, we have sea level high pressure value of 1013 pushing down on you. However, if we were to go ahead and measure air pressure on the top of Mount Everest, you would say that there would be a lower air pressure due to your altitude pushing down on you. So we know that air pressure decreases with altitude. Now we can go ahead and take the same idea of looking at, as we're going up into the atmosphere, looking at pressure in millibars on our x-axis on our chart on our right, and we're looking at altitude in meters. And so we see that we have pressure decreases as we increase with altitude. And this is just another example of what we're talking about. Now, the pressure at Mount Everest, if we go ahead and look at the low pressure at 29,028 feet, is measured at 320 millibars. That's substantially less than the sea level pressure of 1013 millibars. Now, if we go ahead and we look at millibars here on our chart, and we find 320, okay, and we look at our altitude here, you know, that's roughly at the same height as the commercial airlines. You know, it flies at that particular, we're up in the clouds, there's Mount Everest right there, and then at the commercial airlines flies at 12 to 15 meters. So commercial airlines are flying roughly around 250 millibars, and we have Mount Everest, you're standing up there and you're at 320. So pretty darn impressive. So we know that pressure and density, as we move up in altitude, the pressure decreases, there's less atmosphere. So over half the total mass of the atmosphere is below 5.5 kilometers, that's below 18,000 feet. So 75% is compressed below that point, and that's your typical cruising altitude in a commercial airline. So pretty darn impressive. Now, when we talk about wind, wind is basically created because we have an imbalance of pressure. So imagine that we have a hill and a valley. Well, if we have a ball at that top of that hill, the ball is going to want to go ahead and roll down to the valley. So the same thing could be said with having a distribution of high pressure and low pressure. It's not distributed equally. So it's reflecting different temperatures and different pressure. So wind is the horizontal movement of air across the Earth's surface. And wind is named from the direction in that it flows from. And so there's three different types of winds that we'll talk about. We'll talk about global winds that we refer to as primary. We talk about secondary winds, which are highs and lows. And then we have our local winds, such as our tertiary winds. And winds, remember, are a reflection of pressure. So we have unequal pressure due to unequal heating. And we will talk about this in the next section of this lecture.